So welcome to week 5 of 802. When we started off in the very beginning, I told you that the physics of 802 was the foundation for a vast array of technologies. This week we're going to begin our journey from 802 towards those technologies. And over the course of 802 we're going to understand the physics underlying the basic elements of every electric circuit. And the first of those elements that we're going to discuss is the capacitor, and that's what we're going to learn about this week. Later in 802 we'll learn about resistors and we'll learn about inductors, but for this week we're going to be learning about capacitors. But before we can start talking about capacitors, I have to talk about the material out of which a capacitor is made. And we will not be going into great depth on the physics of materials, but I do need to introduce you to the idea that some materials are electric conductors and other materials are electric insulators. You are probably familiar with this division already. What's the basic difference? What is a conductor? Well, an example of a conductor is copper, or aluminum, or gold, or steel, or silver. Conductors are materials in which there are electrons that are free to move. So if I have a conductor here and I apply an electric field pointing this way, the electrons that are free to move in this conductor are going to go this way. Insulators, on the other hand, certainly have lots of electrons inside of them. Every material has lots of electrons inside of them. But in insulators, the electrons cannot move. They're nailed down. They're stuck tightly to an atom, and they can't move. So insulators are examples of materials where if I put some charge here, it stays here. Even if there's an electric field pointing this way, the charge that I put here stays here. So what's an example of an insulator? Well, when I took a plastic rod and rubbed it with fake fur, that was putting charge onto the rod, and the charge stayed where I put it, so that plastic rod is an example of an insulator. Wood is an insulator. Paper is an insulator. This glass that I'm writing on is an insulator. So the materials that we will be talking about in 802 are conductors and insulators. There are actually finer distinctions to be made. For example, we can talk about bad conductors. Yes, there are electrons that move, but there are not very many of them. Those are not typically called bad conductors. They're called semiconductors. And in fact, semiconductors are very important in many technologies, but we will not be doing the physics of semiconductors in 802. For us, it will be sufficient to learn about conductors and insulators. And in fact, in much of what we do this week, we'll be learning about how conductors behave. And actually, if you think about it, everything we've done so far in 802, although I haven't stressed it, has been about insulators in the sense that in 802 so far, we put a plus charge here, and then we put a minus charge there, and then they never moved. That means that plus and that minus charges were sitting in an insulator. We will now be talking about conductors in which electrons can move. And that will be our first step towards understanding how a capacitor works, and the capacitor will be the first building block of modern technology whose physics we will understand in 802.
Conductors are a broad class of materials in which inside there are charge carriers that are free to move. Now we'd like to just represent a conductor as a conducting object, and I'll make it a two-dimensional picture of it. So this is the conductor. Here it's hollow. And we would like to consider what happens in the case of electrostatic equilibrium. Now we have to be careful here because we're not talking about non-electrostatic forces. We're just considering electrostatic forces. So let's take a look at the conductor and let's blow up the interior. So here's our conductor. And the main property of conductors is that the charge carriers are free to move. They'll move around under the influence of mutual electric forces until finally they don't move anymore, and they're not moving anymore when the electric field, let's write, inside the conductor is 0. And this is the crucial condition for conductors at equilibrium. Now, as I said before, we may consider non-electrostatic forces coming from chemical reactions or other types of instances in which you could have a non-zero zero field in a conductor and still have electrostatic equilibrium, but we're not considering that case right now. We're just considering pure conductors and the charge carriers on them. And what we'd like to do is look at the consequences of this condition that at equilibrium, the electric field inside the conductor, the metal of the conductor, if you like, is 0. Well, the first thing we can say is that every point in the conductor is at the same potential. Now, that may seem a little unusual at first, but let's look at the condition. Suppose we have the conductor, and we consider a point A and another point B, and we take any path going from A to B. Well, the potential difference between these 2 points is equal to the integral minus of the electric field along that path from A to B. And because the electric field inside the conductor, I'll just put E in is 0, this integral is 0, and that implies that the potential at every 2 points is equal. So now we have 2 crucial properties about the interior of the conductor. We can call this 1, and we can call this 2. Now, what about the charge carriers? Well, the first question we want to ask is it possible that there are charge carriers in the interior of the conductor, in the metal, at electrostatic equilibrium? So let's take a little piece of this metal. Let's imagine here, suppose we do have a charge Q. And let's blow this picture up. So here's our charge Q. Our conductor is big. And now imagine that you put a little Gaussian surface around this charge. Q Gaussian, radius epsilon. Then we know that electric fields should emanate from this charge. And if this epsilon is very small, they'll go out of this Gaussian surface. And so we can say from Gauss's law that the integral of E dot dA through our Gaussian surface should be equal to 1 over epsilon naught, the charge enclosed. And here in the limit, as epsilon goes to 0, let's see what would happen. Well, the electric field, this is the inside of the metal of the conductor, so this side is 0. And so for surrounding our point charge with one tiny little Gaussian surface, the conclusion is that Q enclosed is 0. So there can't be any charges in the metal of the conductor by Gauss's law. Now, from a physical perspective, that makes sense too, because if there were charges in the conductor, then they would exert forces on all of the other charges in this conductor that are free to move, and the charges will keep on moving. So again, our third key condition at electrostatic equilibrium is that the charge density, so this is rho, is 0 inside a conductor, i.e. there are no charge carriers in the interior metal of the conductor. Keep in mind, we're not talking about this hollow region, we're just talking about the conductor. And those are our 3 crucial conditions for the conductor. 0 electric field, any 2 points on the conductor are at the same potential, and there are no free charge carriers in the interior of the conductor. Now, where are those charge carriers? They're on the boundaries, and we'll study that next.